correct? In the back? Okay, now it is. Great. Welcome back. So we had this great introduction this morning, which unfortunately I missed some of, but getting this sense of all the things that can go wrong. So now we want to try to look on the positive side and think a little bit about what analyses on a database might violate privacy and what analyses might be privacy preserving. And that's a bit hard to think about until you've come up with a definition of privacy, but it's sort of a chicken and egg problem. How do we think about what's the right notion of privacy until we have some sense of what we're trying to do? But hopefully from this morning you've started to get a sense of what might be a bad idea privacy-wise, and that's certainly a place to start, is to say, there are certain analyses that seem really incompatible with privacy goals. And so let's try to build from sort of this bad news that we've heard so far to try to work towards something more positive. So you might think about, okay, so what might I try to promise to individuals whose data appear in a database? What would be a reasonable thing to say to them? And you might try to promise them that you're only somehow going to ask questions that pertain to large populations. Intuitively, that sounds somewhat safe. It's getting away from some of these sort of sparsity issues that I think we've been talking about. Of course, you'd have to formalize it. I just want to hint, though, that even here, even though this sounds like a pretty benign idea, even here you should be careful. So think, for example, I do a survey in this room to find out what's the average salary, and then somebody walks in 1 minute late to the talk. They don't know what we've been up to. There's a slide up that says, oh, we're going to do a survey to find out the average salary in the room. We recompute the average salary, and now everybody who was in the room before knows exactly the salary of the person who just walked in. So even though we've done aggregate statistics, somehow we've still gotten ourselves into trouble. So we want to be careful here. So maybe not. Be cautious. What you've probably gotten from this morning is that deleting identifying information, whatever you might call identifying information, is really sort of a dangerous and ad hoc way to go. Okay, so what can we possibly promise? So let me try something else. Let me try something that's going to take a minute to parse. But what if we could somehow promise folks in the database that access to the output of our computation won't let anyone learn anything about anyone that they couldn't have learned without access? It takes a little while to parse all these anyone's, anything, anyone's. But it sounds maybe pretty good as a guarantee. As an individual, would you be comfortable with a guarantee like this? Is this appealing? Any thoughts? Yes? I see some people who are saying yes, that you would go for this. Is there anyone who has a gut feeling that this is probably not a good guarantee? Yeah. I'm sorry, it's difficult for me to hear. So you're saying perhaps we could even make this stronger and talk not just about learning about individuals, but learning even about larger groups as well. Okay, so potentially it could be strengthened. You might be concerned about sort of properties of groups being learned. So you might ask, well, is it possible, this sounds like a pretty strong definition, or I mean, even before we get to your strengthening of it, is it possible to give a guarantee that sort of meets this notion? Any thoughts? Can we do something like this? I heard yes and I heard no. Yes. Yeah, so intuitively, sure, this is possible. How can you achieve guarantees like this? Well, never output any meaningful information about your data. So the point is, the question shouldn't be, is it possible to achieve a particular privacy notion? But is it possible to achieve a particular privacy notion while simultaneously giving meaningful accuracy guarantees about the computations? And so for the rest of this week, you'll hear over and over in talks about pairings of privacy and accuracy guarantees, because talking about one without the other doesn't quite make sense. It's easy to get good privacy, burn the database. It's easy to get good accuracy, publish the database. So the question is, what can we do that's in between and interesting and meaningful on both sides? Okay, so either privacy or accuracy separately is easy. So what I meant really is, when I said, is this possible while simultaneously doing something useful? And intuitively, in some sense, is this a desirable guarantee? And intuitively, the problem is this really a very, very strong notion. This anything, preventing us from learning anything, is basically preventing us from extracting anything useful from the data. And you could formalize that, but let's try to weaken this a little bit and see if we can make some progress. So what if we could guarantee that access to the output of our computations shouldn't let anybody learn much more about anybody than they could have learned if they'd done that same analysis without that person in the database? This is a slightly different form of guarantee. And again, it takes a little while to parse and a little while to think about whether or not this is something that you might be comfortable with as an individual. But let's try to work with this intuition and try to make it more and more formal to see if it's something we might be comfortable with as a privacy notion. So intuitively, let's try to sort of form some running example for ourselves. Think about, we have data, maybe medical data. So each row is one person's information. It might have some sort of date of birth, some measurements that have been taken, some diagnoses, some diseases, some treatments, hospital visits, whatever it is. And somehow we want to take, in our running example, we want to take a database like this and compute something on it and make that output public. And we're thinking still about what we might promise to individuals in this database. And intuitively, we can pretty quickly realize that probably randomness is going to be important for us. Intuitively, if we are going to be running deterministic algorithms, we're going to be encoding a lot of information in those answers. So probably what we want is something that gives us about the right answer, but somehow randomized and so has some distribution around the correct answer. And so trying to push more and more in the direction of a formal guarantee. So maybe what we want to do is promise to individuals, if you were to leave the database, that no outcome would change probability by very much. So thinking from the perspective of an individual, if we could guarantee something like this would say basically, well, we're going to get about the same results regardless of whether you're in or outside of the database, and so you don't have a lot of incentive maybe to withhold your data, maybe sort of if you have concerns about the computation, those concerns really aren't affected by whether or not you participate. So let's try to push this a little bit more towards a formal definition. So for that, we're going to need a model. So this is going to be the model for most of the rest of this week with some variants. So basically, we're going to think of a database as a set of possible entries, or rows, one row per person. And those rows are drawn from some set of possible entries. So there are possible rows of medical information that could exist. A database is just some set of such rows. We'll commonly use a somewhat non-compact and somewhat initially non-intuitive representation for a database, which is a histogram. So we'll think about representing that set of rows as actually a vector, saying for every possible row, how many times did that appear in our database? So obviously this is not something you would do if you were trying to represent your data in the real world, but it will be a useful representation that will appear commonly in the literature. So I want you to be familiar with thinking about a database as represented that way. Okay, so given this representation of a database, let's try to maybe nail down a formal version of these hand-wavy notions that I was trying to convince you of before. So let's think from the perspective of the analyst. She has access to a database, and there are many things she might want to do with it. We don't really want to restrict her very much. Maybe she's interested in doing some sort of learning, she's fitting a model, she's computing a handful of statistics. Maybe she wants to produce data that looks like data, and let researchers do what they like with it. We don't want to restrict our analysts too much, but somehow she wants to take data and produce some outcome, while simultaneously preserving the privacy of individuals. And informally, her goal is going to be then to design randomized algorithms that map from database space into some outcome space that somehow are masking small changes in the database. So this masking small changes is intended to capture this intuition that I've been trying to develop here, that if we can get the algorithm to behave approximately the same, regardless of whether or not you provide your data to the algorithm, that might give you some notion of privacy. And so building on this, we need some sort of notion of small changes in a database. And so the notion of neighboring databases that we'll work with for the most part is we'll talk about databases that differ by the addition or removal of a single row. So just think of it as the database with me versus the database without me. And so given this notion of neighboring databases, we can now finally get to the notion of differential privacy. It's an idea that comes out of a number of papers, sort of in the 03 to 06 range, so still relatively new, and you have two of the originators of this concept here for your school. So differential privacy is a parameterized notion of privacy. So we'll talk about, for example, epsilon parameterized differential privacy. And it's a property of an algorithm, a property of a mapping from database space to outcome space. So we talk about that mapping having privacy. And we say that that mapping preserves epsilon parameterized differential privacy if for any two neighboring data sets that differ by the addition or removal of a single row, and any subset of the outcome space that you might be interested in or concerned about, we say that the probability that that algorithm maps the first database into that subset of the outcome space is approximately the same as the probability that that algorithm maps the neighboring database to that subset of the outcome space. Okay, so if you've seen this before, no big deal. If you haven't seen this before, it's a bit to take in and parse. So let's try to make sense of what's going on here. So the first thing that might strike you as odd in this definition is it doesn't look like it's a symmetric definition. But I'll try to reassure you first that it really is. So why might you be concerned it doesn't look symmetric? I've put x1 on the left-hand side of this inequality and x2 on the right-hand side. But I said this had to hold for any two neighboring data sets, x1 and x2. Therefore, it also has to hold for x2 and x1. Okay? And so other things that might be a little hard to parse, maybe this e to the epsilon thing, which I just read as approximately the same, is a little hard to think about that. Just think about it as a multiplicative 1 plus epsilon. So just think about this as a guarantee that says that the probability mass that our algorithm places on any subset of its outcome space needs to be multiplicatively close under any two neighboring databases. And notice that there are a couple of quantifiers that are really key in this definition. So this is a definition that is constrained to hold for any two neighboring data sets, and we're going to give this guarantee of closeness for any subset of the outcome space. So it's a very strong definition because of these two quantifiers. And so we're going to spend a little bit of time trying to get comfortable and familiar with this definition. I just realized I have nothing that has the time on it in front of me, so let me acquire something. And and trying to understand what properties this definition has, and to what extent this might actually be a sufficient or reasonable or desirable notion of privacy for us to work with. So just working with this idea a little bit and thinking about what its consequences might be for a simple computation, let's return to this illustration where we have medical data and we want to do a simple statistical computation. Let's try to figure out what percentage of people in our database have cancer, something like that. So intuitively, what differential privacy is going to say is, well, if my algorithm samples from a particular output distribution, given a particular input database, then all of a sudden I'm constrained on how I behave on neighboring databases. Because if I sample from this distribution on this database, well, in particular, if I were to look at the database without Ellen Jones, then I would be required to behave almost exactly the same. I would be required to produce probability masses that look very similar. So this is sort of the intuition that we're trying to capture here. Thinking maybe from the perspective of an individual who's trying to decide whether or not to allow her data to be used in a computation that's guaranteed to give this differential privacy guarantee. Well, how do you go about thinking about a question like this, whether or not to provide my data to a computation? One thing that you might do is you might think about, well, I have some particular concerns. There's some things that might happen as a consequence of this computation that I might be worried about, that I might be unhappy about. So think about if this is a computation of medical data, maybe I'm concerned about consequences in terms of my insurance rates going up or my children being discriminated against because it turns out I have some disease that has a genetic component to it, something like that. So you could think about sort of all future worlds that could occur and all bad things that could occur in these future worlds and say, okay, man, I don't know if I should hand over my data because there are all these different possible bad outcomes that could happen. I don't know how likely they are exactly. But if this computation is going to be done in a fashion that guarantees differential privacy, you actually don't have to think very hard because you immediately have this guarantee that the probability of those bad future worlds is almost exactly the same regardless of whether or not you provide your data to the computation, and regardless of whether or not you lie about your data. So from the perspective of an individual, it's saying, you might as well participate, perhaps. It's a little bit of a stretch to get to that interpretation. It's an interpretation that we'll push later in the week. But it is giving you some guarantee from an individual perspective about what might happen as a consequence of a computation. We'll also, many times during this week, be relaxing the notion of differential privacy to get us another parameter. So we not only have this epsilon, which is controlling these multiplicative differences in probability mass, but we'll also talk about epsilon delta, parameterized differential privacy, where we allow ourselves an additive delta slack. So how to think about an epsilon delta versus an epsilon zero, or I sometimes just call that epsilon differential privacy. Well, one thing to point out is that these are really qualitatively different guarantees. So when I didn't have that delta there, it was impossible for me to go from a zero probability event to a non-zero probability event. So if some outcome never happened under a particular database, then that outcome could never happen under any database if my mechanism were to guarantee differential privacy with the epsilon parameterized version. If I allow myself this delta, which we'll typically think of being sort of cryptographically small, then we have this sort of qualitative difference because it's now possible to go from zero to non-zero. But intuitively, and we'll sort of build intuition for this as we work with this relaxed notion of differential privacy over the week, intuitively think of it as the epsilon version of differential privacy, plus you're allowed to throw a little bit of probability mass wherever you want to in order to make things easier. And it turns out to give us actually, in some cases, significantly more power to get good privacy accuracy trade-offs if we allow ourselves that delta. And that's why we're going to be willing to do it in some cases. Okay, so in some ways, what stands out about differential privacy as a privacy notion is that it's not a property of a particular number or a particular output. I can't do a computation and get the answer 5 and say 5 is differentially private. I can say the process that produced this answer is differentially private. So if you're accustomed to thinking about privacy through a number of sort of other sort of ad hoc techniques that they might be familiar from the statistics literature or elsewhere, it's a bit of a shift to think about privacy as a property of the mapping rather than of the output. There's no way to say that a particular number or a particular sanitized database is private when we're thinking about privacy. In a differential privacy sense, it has to be the process that generated it that's private. And by moving from thinking about the output to thinking about the process, we actually get a huge win. What is this huge win? Well, all of a sudden, we get ourselves out of the business of modeling the adversary. And as you've seen this morning, modeling the adversary is very difficult because sometimes your adversary is Vitaly and he's quite smart. And because you don't know what adversary is going to be out there and what data is going to be out there and how that's going to change a week from now, a month from now, a year from now, 10 years from now. And with privacy and privacy issues, we really want to guarantee that the output of our mechanism, the output of whatever it is that we produce and publish, is private not just today, with today's notion of an adversary, but private forevermore. And that's what you get here. All of a sudden, we're no longer modeling the outside information that's available to an adversary. We're just talking about guarantees of a mechanism's behavior when comparing with or without a particular individual, except for all possible neighboring databases. Again, and we're not thinking about the computational power of an adversary or making assumptions about how the adversary might attack us and the output that we produce. So all of a sudden, we've gotten ourselves out of this really messy business of thinking about who we're up against, and with this very clean model to work in. So now, I'd like to give you a bit more of a sense of some of the properties of this differential privacy notion that make it a really nice guarantee. And first, well, before I do that, you might have in the back of your mind, wow, this sounds like a really, really strong privacy guarantee. Is this even achievable in any meaningful fashion? The good news is, yes, that's what this week is about. Rest assured, we're going to get there. We're actually going to do quite a diverse and sophisticated set of computations subject to this sort of guarantee. So before we start doing that, though, I want to convince you that it's got some nice properties. And oh yeah, another form of convincing you is, anybody use the Chrome browser? You're already using differential privacy. Anybody have an iPhone? You're already using differential privacy. So more and more, it's a notion that's out there, it's being deployed, and something we can return to is questions of sort of how is it being deployed in these various applications that have gotten a fair sort of high profile, and what are the important aspects of the guarantee that they're giving in these situations. But really, this is something we can do. Okay, so what are the properties that I want to tell you about? So the first one that I want to talk about is group privacy. And intuitively, this is just a guarantee that says, well, differential privacy was talking about neighboring databases that differ in one person's information, but you might care about, well, what if my database were to change more than just in one row, but to change in a handful of rows? What if I wanted to give privacy not just to one person, but to a handful of people? And one of the nice things about the differential privacy guarantee, and we might actually do this proof later this afternoon if we have some time for it, is that you can immediately take this guarantee for one individual and see that it translates into a guarantee this, sort of multiplicatively k worse when you're thinking about privacy for groups of size k. So that's just the intuition there for group privacy. The second property that I wanted to get to is post-processing. And I find this is the property that either strikes you as completely obvious or is completely sort of mystical and mysterious, and people really can go either way. What post-processing intuitively says is that if you take a mechanism that's differentially private, and then you subsequently do whatever you want to with the output, you think about it really hard, you apply whatever smart ideas you can come up with now or any time in the future, nothing you do later on can break the privacy. So either that sounds totally obvious to you if you've somehow internalized the sort of mathematical notion of differential privacy, or this sounds totally magical because somehow before we thought about differential privacy, post-processing was a serious concern. Because if you have sort of a more ad hoc notion of privacy, I'm going to delete these entries and these that seem pretty sensitive, I'm going to sort of cluster some of my data together, and I'm going to cross my fingers, there was no guarantee that somebody wouldn't be able to come along and do something smart and break your privacy. But this post-processing guarantee really tells us that if we do something that's differentially private, it's private forevermore. We can publish the results, and we can sleep well at night. That's a really nice thing to have. And this we may actually, depending on timing, we may actually come back and do this. It's a nice sort of first or second proof of differential privacy to see. But I'll get through some of the properties first, and then we'll see how we're doing on time. We'll pick a couple of these to maybe do together as a proof. The next property that I want to highlight is, in some sense, the key property that is the reason for the differential privacy success story. So what do I mean by composition when I say composition? So there are a few different versions of composition theorems. I'm going to state for you first here the sort of the simplest version. We can work up to more and more complex versions. Kobe, I think, is going to give you sort of the most sophisticated version that we know of a composition theorem tomorrow. But intuitively, what a composition theorem says is it says if you do something differentially private, and then you do something else that's differentially private, that those two things together still give you some sort of guarantee of differential privacy. Now you see degradation in the parameters, and what sort of degradation in the parameters is part of what we're looking at when we're looking at these composition theorems. And so the sort of simplest version of the composition theorem just says, if you do a bunch of things in a row that are epsilon delta differentially private for various epsilons and deltas, one thing you can do to understand the privacy guarantee of the whole sequence of computations is to add up the epsilons and add up the deltas. And that already gets you a lot of mileage, because already now it gets you into a place where differential privacy allows you to build sophisticated privacy-preserving mechanisms, much like you would build with Legos. You can create these nice differentially private building blocks, and from them, you can assemble these much more sophisticated mechanisms and towers and machines, and all you have to do is a simple accounting at the end to figure out how all the privacy guarantees add up. And that's really a big deal. Another aspect of composition theorems that we'll get to more tomorrow is that these types of theorems actually hold up even under adaptivity. So even if I do a differentially private computation, I look at the results and I think really, really hard. And then only after having looked at the results and thought really hard about them do I pick my next computation. Then I do something else that's differentially private. Even if I have that adaptivity and the sequence of computations is not fixed in advance, still you can get these sorts of composition theorems. And that ends up being really, really powerful. And it will have really nice consequences that we'll start to see towards the end of the week. Okay, so those are the sort of high-level properties that I wanted to get into for differential privacy. So I think what we'll do is we'll come back to proofs of some of these in a couple of minutes. But first, let's sort of check our intuition and then think about sort of a first differentially private mechanism. So first, for checking our intuition, just when you're thinking about differential privacy, is a big delta good news for privacy or bad news for privacy? I heard good and I heard bad. Bad? Somebody who said bad. Why? Why are big deltas bad news? Somebody said bad loudly and boldly. Yeah. Where was it? Okay. Yeah. So why? Why would a big delta be bad? Okay, but sort of even more intuitively, what is a big delta allowing you to do? Yeah. Okay, so why would a big delta be allowing you to leak more data? You're totally right. I just want to get more and more into your thinking. It's allowing you more difference. Yeah, okay. So you're saying you're allowed to change the output more significantly when you have bigger delta. So intuitively, that makes the outputs look less similar, and so there's less privacy. Okay, yeah. Yeah, good. Okay, so what about epsilon? Is big epsilon good news or big epsilon bad news for privacy? It's a little harder to think about because you got that e to the epsilon going on. Which way does that go? Somebody else who hasn't thought about this, yeah. Is that the start of a hand over here? Yeah, so is big epsilon good? Bad. Bad, okay. I heard a bunch of bads. What are those bold bads? Why? Yeah, go for it. Okay, so what I think I heard, I didn't hear all of the words, sorry, from the back of the room, it's hard. What I think I heard is that you said when your epsilon gets bigger, you're multiplying by a bigger number, and so that's allowing you more difference, again, in how these distributions look. So you have sort of more ability to change your output when you're moving from one database to a neighboring database, and that lets you reveal more. Yeah, okay, yeah, more. Right, so as your epsilon gets bigger and bigger, then you have sort of less and less constraint on how you behave. Yeah, good, okay, so we're starting to get a little bit of intuition for how these notions are working. Okay, so let's see our first differentially private algorithm, and then maybe we can go back to some proofs of these properties. So this first differentially private algorithm actually completely predates differential privacy. So what is randomized response? Forget what's on here for a second. So what's the idea here? So randomized response is a tool that was developed in the social sciences context when I'm in a situation, so say I'm a social sciences researcher and I want to understand the prevalence in a population of an embarrassing trait. I want to know what percentage of people in this room are HIV positive, or have cheated on their spouse, or have ever cheated on an exam. And somehow I have to figure this out. Now I could go around and ask you one by one, have you ever cheated on an exam? Have you ever cheated on an exam? Have you ever cheated on an exam? And even if I didn't do this in public, I have a feeling the statistics I get are not going to be totally accurate. And so the idea behind randomized response is to give people some sort of plausible deniability when they respond to a question like this of a sensitive nature. So everybody has some private bit. 1 if you've ever cheated on an exam, 0 if you never have. I want to understand the prevalence of that bit in this room. So what I can do in order to do that is tell you to run this protocol. So you're going to run this protocol. It's very simple. People have done it. And you're going to privately flip a coin. I can't see that you're flipping the coin. Nobody can see that you're flipping the coin. Nobody can see, but you can see the outcome of the coin flip. If your coin comes up tails, you're going to respond truthfully to my question. So if I ask you, yeah, have you ever cheated on an exam, and the truth is yes, you're going to say yes. If the truth is no, you're going to say no. If your coin came up heads, however, your true bit is no longer going to play into what you tell me. Instead, you're going to secretly flip a second coin. Again, nobody can see that you're flipping the coin, and nobody can see the outcome of that coin flip. And you're going to respond to this sensitive question simply with a response that's completely determined by that second coin flip. So you're going to say yes if it came up heads, no if it came up tails. So intuitively, this is giving you some sort of plausible deniability. So if you say yes to the sensitive question, oh, of course, it was the coin talking, right? But when I do this across a large population, like I have in this room, then actually I can back out from the statistic that I gather a pretty good estimates of prevalence in the population. Now at the individual level, I don't have a very good sense of whether or not you've ever cheated on an exam. But what I care about is the aggregate. Make sense? Okay, so why is this simple protocol from 1965, why is this differentially private? Well, let's think about it a little bit. So what do we have to do in order to do a proof that a mechanism is differentially private? Well, we need to look at these. We had all these frawls and things floating around in there. What do we need to look at? We have to somehow look at a comparison of the probability that we're going to say yes, given that the truth is yes, versus probability that we're going to say yes, given that the truth is no, and no given no, and no given yes, and I have to figure out how the probabilities all line up. So first of all, I want to highlight, I'm doing something a little bit non-standard here that doesn't quite fit with how I presented things to you so far, because what's my database here? My database is one person's information, just their bit of yes or no. And what's my neighboring database here? It's not quite what I told you it should be before. Now it's just when you have your bit flipped. And this issue of whether a neighboring database is one person changing their data or adding or removing somebody is one that will plague us a little bit through this week, but give me the benefit of the doubt on the fact that I've just sort of tweaked the notion of privacy slightly here, and let's do this comparison of probability of outcomes given the two possible input databases. So what's the probability that I'm going to say yes under this mechanism, given that I truly have cheated on an exam? What's the probability I'm going to say yes, given that the truth is yes? Thoughts? Pardon? Well, half the time I'm going to respond truthfully. And so I'm going to say yes. The other half of the time, I'm going to let a coin decide. And so that's another quarter, so 3/4. All right. And what's the probability I'm going to say yes, given that the truth is no? 1/4. Yeah. So, half the time I'm going to say no truthfully, and the other half the time I'm going to let the coin decide. And so we have this ratio of 3/4 to 1/4. You do a similar analysis for responding no, and you see you get a ratio of 3. And now, because we had that funny e to the epsilon in our multiplicative guarantee, that says that randomized response is log 3 differentially private. Now, what do you make of a guarantee of log 3 differential privacy? Probably not much, particularly at this point. You don't know how to interpret this guarantee. Is this a good guarantee of privacy? Is this a satisfying guarantee of privacy? Would you be willing to use this mechanism if the question were about cheating on your spouse? Would you be willing to use this question if it were something more innocuous? I don't know. But at least we now have evidence that there are mechanisms that achieve this somewhat sort of unfamiliar definition that we've been trying to get our heads wrapped around. So what if I wanted to make this protocol more private? What could I do to it? More coin tosses, what does that mean? I heard that from somewhere, but I didn't see where. So yeah, so what does that mean to do that more? Yeah, so if I use a biased coin and put less probability mass on the truth and more probability mass on the random outcome, that intuitively gives me more privacy. And where would you see that play out in our analysis of the privacy guarantee? So if I were using a biased coin, what would be changing here in my analysis? Yeah, so what would be happening to these probabilities? Would the sort of the numerator and the denominator, would they be getting further from each other or closer to each other? Closer, further, oh no, both. What would they be doing? Closer, further? Oh no, both. Okay, all right, so what's the argument?
We always respond randomly.
Good, okay, so yeah, so so to get us some confidence in your answer, you push it to the extreme. So we said our first coin is going to be so biased that we never actually tell the truth. Okay, great. And so if it's so biased that we never tell the truth, what are our two probabilities? A half and a half. So they got closer. Okay. So yeah, the closers win. Good, okay. So we have a guarantee now of differential privacy. You want to find out how many cheaters we have in the room? It's fun to run. Should we do it? Okay, since we have a big room, I might only run it like in the first half of the room, just to get through this. Okay, so here's how we're going to run this. Think of a phone number, one of the first phone numbers that you learned as a child, but not your home phone number, because somebody else in the room might be able to figure that out. But some other, a best friend, a grandparent, somebody. Think about a phone number that you learned as a child. You thinking about that phone number? You have a number. Hopefully, you're not so young that you've never learned a phone number. Everybody has a number in their head? Okay, now focus on those last 2 digits of your phone number. You're old enough to, okay, so make up a phone number, okay. But you need to have a number in your head right now before I tell you anything else. I need everybody to have a number, at least with 2 digits in it, in their heads. Have you got it? Good, okay, so now I'm going to tell you how to interpret that number. So I'm going to drop everything except the last 2 digits. So you have a 2-digit number. Everybody still has one? Good. Okay, so this first one is your first coin flip. Even is heads. Odd is tails. The second number is your second coin flip. Again, even is heads. Odd is tails. This is surprisingly hard to do, this conversion. Okay, so you had a number. Now carefully convert it into 2 coins. Don't think too hard about anything else yet. Okay, you may need to write this down privately. Make sure you destroy the evidence afterwards. But write yourself a little note that tells you what your first coin flip is, what your second coin flip is. Okay? If you can do this in your head, I'm impressed. If you can't, write it down. Everybody in good shape? You have 2 coins. Yes? Anybody not have 2 coins? You still can, okay, get yourself coins. Anybody not have coins? Okay, Adam has figured his phone number out. Good, okay, so now I'm going to ask you a question, which is, have you ever cheated on an exam? So now you have a yes or a no in your head, and you're going to, in your head, run this protocol. Again, surprisingly difficult, but I think you can do it. So you take that yes or no, and you flip your first coin. If necessary, you flip your second coin. And you come up with a yes or a no. Has everybody got it? Forget everything that generated this final yes or no. Forget the process. You just have a yes or a no in your head. Good? Everybody has a yes or a no. Does anybody not yet have a yes or a no in their head? Everybody has a yes? Okay. Make your yes or your no. All right, who's gonna record answers for us? Somebody. Are you willing to be our answer recorder? You have a pen? You have a pen, and you can hear well people in the room? Okay, so we're going to go around, and everybody's just going to say yes or no. You're going to count for us the number of yeses, the number of nos. Okay, can you do that? All right, great. Everybody ready? Okay, I'm going to go around the room. Everybody's just going to either say yes or no.
Yeah.
Shout it.
No. Yes. No. Yes. 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 No.
John,
No. Yes. Yes.
you recording? Adam.
Yes. Yes. No. No. Yes. 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 No. Yes. No. 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 Yes. Yes. No.
Yes, okay.
Yes. 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 No. No. Yes. 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 He's not counting.
You stopped counting? What? You stopped counting? Come on. Did you stop at a particular point, or were you just pretending the whole time? Okay, come on. All right, I will keep track. I'm just slow. I thought somebody else would be more. Okay. All right. So I'll do it up here.
Might just get put up the hands if they had yes, and otherwise hands.
Okay, we'll do hands, but it's more fun to go around the room. Okay, fine. We'll do hands. All right. Yeses. How many have we got? Man, there are a lot of you guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Some of you are raising your hand very low. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. I think I got that about right. Okay. Did I even count in order? Was anybody checking? Okay. How many no's were there? All right, good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 36? Did I get it? I might be off by 1 or 2, but we get the idea. Okay. So what do we make from this? Nothing? No. So what do these numbers mean? Let's assume that you actually all did follow the protocol. I know it was hard. There was a phone number, blah, blah, blah. Let's assume you all succeeded in following the protocol. What do we make from this? Yeah. 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 Yeah, good, okay. So the number of people who said yes is somehow going to be, well, sort of from this protocol, what? Well, what can I say? Or maybe it's easier to think about percentages. It's going to be sort of a half times what? Times percent true yes, plus a half times what? A half. Okay? So how do I interpret my 45 out of 81? Somebody who's either good at this in their heads or their phones or their graphing calculators or whatever you have in front of you. How do I interpret this? So we had this percentage who said yes. So you're going to take this number and you're going to subtract out a quarter, and then you're going to multiply by 2, and you're going to get what? What number? Percentage of cheaters is 55%. Okay. There you go, guys. Make of it what you will. Okay, so we've run our first differentially private protocol. Mostly it's kind of fun. So now let's go back and think about doing another proof of privacy. So this was sort of our first proof of differential privacy. Let's go back and maybe let's do a sort of simple composition theorem. Okay? So I've run this a lot of times. Half the people cheat. That's just the way it is. Okay, so what theorem do I want to do? So let's just sort of do the simplest version of a composition theorem, which is going to be, I'm going to have 2 pre-selected computations that I'm going to run, M1 and M2, that are each differentially private. So M1 takes a database, returns something in some scripty R outcome space, and we're going to say it's epsilon 1 differentially private. I'm going to leave out the deltas, so I'm just going to do epsilon comma 0 differential privacy for this sort of simplest version of composition. We'll get more sophisticated. And I have some other mechanism, M2, which also takes in a database and maps to some other scripty R outcome space. And we'll say that's epsilon 2 differentially private. And what I'd like to say, then if I take this sort of composition that takes in a database and does the obvious composition, by running M1 on the database, and outputting the answer, and running M2 on the database, and outputting the answer, that it's epsilon 1 plus epsilon 2 differentially private. So that's the theorem that I'd like to prove. It's sort of the simplest composition theorem. How is the board in terms of visibility from the back? It's so-so. I'll keep trying to narrate it. It's not a very big board, though, so I don't want to write much bigger. Okay, but if it's really incomprehensible also because of my handwriting, please speak up. Okay, so how would we go about proving a theorem like this? How do you show that if we have 2 things that are differentially private, then the composition would be differentially private? So again, we have to think back to what it means for something to be differentially private. We have all of this quantification going on. So what are the things that we need to be able to compare? Well, somehow, we want to be able to say, for any 2 neighboring databases, that something in particular is going to happen, and that something in particular is going to be for any particular outcome that we might be interested in, or subset of the outcome space, the probability mass that we get mapped there is going to be almost exactly the same. So now, I'm going to use a theorem that's pretty easy to prove, but maybe we actually ought to do it this afternoon, because I'm not going to prove it for you, which just says that if I'm in epsilon differential privacy world, and I'm thinking about the quantification that I have in that theorem, so for all neighboring databases, for all subsets of the outcome space, that actually I just need to prove this theorem for all neighboring databases for all individual discrete outcomes, if I have a discrete outcome space, and that's equivalent. So I can look just outcome by outcome and prove my theorem so that it holds for all outcomes, rather than thinking of all combinations of outcomes, all subsets of the outcome space. And then intuitively, you can see that this is not going to be more than a couple lines of a proof to show that that's an equivalent notion. Not the same if you have a delta. Be careful. Okay, so What I need to do is I need to say, let's say I have two neighboring databases, arbitrary. And this is sort of, I'll be very explicit now, and you're going to do this over and over again, and sort of the form will get familiar. So you have two neighboring databases, and you're going to fix some outcome of interest. Why is this the outcome space that I'm focusing on here when I'm writing my proof? Why am I not focusing on R1 or R2? Why am I focusing on R1 cross R2? Well, this is the mechanism that I want to prove is differentially private. So I'm interested in the outcome space of this mechanism here. Okay, so I've fixed neighboring databases, I've fixed an outcome of interest, and now what am I going to compare? Well, I want to compare the probability that my mechanism M1, M2, when given X, outputs R1, R2, versus the probability that my mechanism M1, M2, when given Y, outputs R1, R2. Okay. What do I know about these probabilities? Not much. So what can I do here? Since I didn't have adaptivity getting in the way, these are independent, right? So, the probabilities that they go into making up this probability that I get R1, R2 is just what? Probability that the first mechanism gave me R1 times probability that the second mechanism gave me R2. Good. So probability that M1 of X gave me R1 times probability that M2 give me R2. Check that I'm not going to get anything wrong here. Okay, so M2 of Y gave me R2. Now what? Again, I don't have a lot of tools at my disposal. What can I do here? What do I know about these probabilities? They have a relationship because these were differentially private mechanisms. So what can I say? How can I bound this ratio? Exactly. E to the epsilon 1 times e to the epsilon 2. And I'm done, or am I not done? Did I finish my proof? So there's one thing that I want you to check. You think you're done with your proof of differential privacy. Check that what you did was symmetric. So you had two neighboring databases, an X and a Y, and you picked, the X went on top and the Y went on bottom. Check that there wasn't an assumption built into them that made the X different from the Y in some way. So was this symmetric? Did I just pick an arbitrary one? So we're good. We're done. Okay, so we have another proof of differential privacy. We'll see more of them as we go along. I think that's the end for now.